Hi everyone. In this and the next two lessons, I'm going to give a brief introduction to micromechanics and its application to multi-scale analysis in structural geology. My goal is to give you sufficient background for you to learn the topic yourself. More detailed treatment of the topic is in the lecture notes, specifically in chapters 10 to 15. Micromechanics is a most recent development of continuum mechanics. It all started from Eshelby's fundamental work. So today we are going to talk about Eshelby's fundamental inclusion and inhomogeneity problems. Eshelby has made fundamental contribution to material science. He is best known for solving the elastic field of an ellipsoid in an infinite elastic body. His papers published in 1957 and 1959 are probably the most cited papers in mechanics. And his work leads to the development of micromechanics, which is continuum mechanics for heterogeneous materials. This picture of Eshelby was taken from biographic memoirs of fellows of the Royal Society. It's a paper published by Beerby. Incidentally, Beerby, Eshelby, and Kondo published a paper in Tectonophysics in 1975. That was the first paper on the deformation of viscous ellipsoid in ductile flows. Let us now talk about Eshelby's inclusion problem. Imagine an elastic body, a uniform elastic body extending infinitely in space. Eshelby asked the question, what is the elastic field of the entire body if a region inside the body changes form? He called the region inclusion. The region has the same mechanical property as the outside, so the entire body is uniform elastically. The region omega changes form, which means it changes shape and or volume. Eshelby solved this problem by a few steps of what he called transformations. If we cut out this inclusion is going to complete its form change. So it's going to undergo a transformation strand, E star. Eshelby called this change a transformation strand, but later on this is called generally eigenstrand. The entire elastic body now has a hole. The entire body is stress-free, strain-free, except that it has a hole in it. Step 2, apply a surface traction on this inclusion so that it returns to its original shape. So the inclusion is stressed, but the total strain is 0 because it returns to the reference state. Step 3, place this inclusion back to the hole and glow the interface. So the interface is perfectly bounded. The outside material is still stress-free, strain-free at this step. Now we remove the surface traction. Removing the surface traction mechanically means apply a body force along the interface to cancel the traction force. At this step, we return to the original problem. In the end, the stress and the strain field in the body is what is produced by the body force along the interface. We can summarize the stress, strain, and the interface state corresponding to the respective states in this table. So step 1, we remove the inclusions. The matrix is stress-free and strain-free. The inclusion is stress-free. The inclusion attains its transformation strain. It's a free state, no stress. However, it has a strain. It has eigenstrain. The interface is force-free. In step 2, the matrix remains stress-free and strain-free. The inclusion has stress. So the stress is the elastic modulus multiply the strain. Remember, the strain is the inverse strain of eigenstrain because It's a deformation, bring the inclusion back to the original state. So the strand applied is actually negative, the eigenstrand. That's the internal stress in the inclusion. At this state, the strand is free. There's zero strand because the strand is measured with respect to the original state. So it's identical shape and volume, no strand. Surface traction on the inclusion surface is like the stress field projected along the normals. N is the normal unit vector at every spot of the interface. Now in step 3, when we put it back, the matrix is still stress-free, strand-free. The inclusion is still the same state as in step 2, even though the interface is bounded, but the inclusion is still acted upon by a surface traction. So the interface is still force-free. Finally, in step 4, we remove the surface traction. That is equivalent to apply a body force along the interface that is negative the traction. That is this. The material outside the region is stressed, and the material within it will also be stressed. So with those transformations, the problem thus becomes the elastic field caused by the body force distribution along the interface. The problem becomes a body force problem, and that can be solved elastically. So the inclusion problem now is transformed to the elastic field caused by a body force distribution on the interface, and the body force distribution on the interface is this one. In session 2, when I talk about the stress, I touched upon very briefly on the idea of solving elastic problems by the Green functions method. I didn't go to any details. I want to revisit that concept. Still, we're not going to get to the details. So the Green function expresses the displacement at a location caused by a point force at another location. Green function is a function that relates the displacement field at the location x derived from a body force at the location x prime. If a body is acted upon by a body force distribution or by many point forces, the total displacement at a point is going to be the integration of all the body force acted in the entire volume. Apply this concept to the solution of the inclusion problem. The confined state of the inclusion has a displacement field like this. It's this relationship, except that we replace the point force by the point force along the interface. So the integration is along the boundary of the inclusion. This is called the integral formalism. Although the integral formalism may appear formidable, it's very convenient in numerical computation. And the Green's functions for an isotropic infinitely extending elastic body was already known. The Green functions in anisotropic bodies are expressed in integral forms. So the Green functions method provides a unified formalism towards the elastic problems, and are fundamental in the solution of Escher-based inclusion problems, which are pivotal to the development of micromechanics. So now the inclusion problem can be solved. The displacement field is expressed by this integration. Every term is known. The body force is expressed as a function of the eigenstrand. Green's function for the body is known. For isotropic material is known since 1848. And for anisotropic materials, it can be expressed in an integral form. With the displacement field known, the strand field is known. Just take the derivative, the special derivatives, we get the strand field and the rotation field as well. So formally, the strand field within the inclusion can be expressed by this expression, and the rotation by this one. S and pi are two fourth-order tensors, and they are functions of the elastic stiffness of the material and the Green function. Therefore, Eshelby's approach did not just solve one specific problem, but provides a powerful means to solve a type of problems, because these tensors can be expressed and tabulated and with numerical evaluations developed, and they can be used for many similar problems. A significant result of Eshelby is also the proof of the following statement. If the matrix is uniform and infinitely extending, if the inclusion is ellipsoidal, the strain and the rotation in the inclusion is uniform. S and pi are called Eshelby tensors. We already have the strain field and the rotation for the inclusion. What is the stress at the confined state? The confined state of the strain is expressed by this expression. It is important to realize that the corresponding stress state is not the elastic stiffness multiplied the confined strain. The reason for that is EC, the confined strain state, is not entirely elastic strain, because EC equals 0 does not correspond to stress-free state. Instead, the stress-free state corresponds to the eigenstrain state. Because of this, the confined stress in the inclusion is the elastic stiffness of the material multiply the strain difference, the EC subtract the eigenstrain. Again, the reason is because eigenstrain state is the stress-free state. Now we move to Eshelby's inhomogeneity problem. A heterogeneous inclusion is called an inhomogeneity. So if the region has the same elastic stiffness as the outside, Eshelby call that an inclusion or homogeneous inclusion. If the region is distinct, rheologically it has a different elastic stiffness, it's an inhomogeneity or a heterogeneity. The inhomogeneity problem is stated like this. What is the stress and the strain field inside and outside an inhomogeneity embedded in a uniform matrix subjected to uniform stress and strain at infinity? Eshelby solved this problem by the brilliant equivalent inclusion method. So the two most important ingredients of Eshelby's methods are point force method, which leads to the application of Green function, and the equivalent inclusion approach. Let us look at Eshelby's equivalent inclusion approach in detail. This is our objective. This is what we already solved. How do we use this solution to solve this problem? Here is the method. Let's call the strain within the inclusion E. The elastic stiffness is C1, which is different from the elastic stiffness of the medium. The medium is Cm here. The remote strain is Em. Remote stress is capital sigma. We can regard the strain within the inhomogeneity as the sum of remote strain plus another part called EC. The external field can also be considered as the sum of a uniform strain field caused by the remote stress plus an EC component, which varies in space. If we can find an inclusion, that is, equivalent inclusion, it has the right amount of eigenstrength such that it will have the same stress as the inhomogeneity. If the inclusion has identical shape and also identical internal stress as the inhomogeneity, then it's going to cause the same stress and strain field throughout the body. So the problem becomes how to find this EC. The way to find that is simple, because the stress in this inhomogeneity is this: elastic stiffness multiply the strain. The stress in this hypothetical inclusion is this. Make that two equal, so the stress in the inhomogeneity is equal to the stress in this hypothetical inclusion. Using this equation, we can find the right amount of eigenstrength such that this inclusion can replace this inhomogeneity and produces the same stress and strain field throughout. That is the equivalent inclusion we are looking for. Rearrangement of this equation leads to these two relations. So the strain in the inhomogeneity is related to the strain in the remote field. A relationship for the elastic rotation can also be written. This package is packed into a fourth order tensor here, A. Using Hooker's law, we can write the stress in a relationship like this. We call these relationships partitioning equations for elastic materials. So strain partition relationship is strain within an inhomogeneity is related to far field strain by this strain partitioning relationship, rotation by this relationship, and stress by this. These are partitioning equations. Because linear elastic equations have similar forms to linear viscous equations, so we can write similar partitioning equations for Newtonian materials. Replace the strain by strain rate. So the strain rate within an inhomogeneity is related to the remote strain rate by a strain partitioning tensor. The vorticity within an inhomogeneity is related to the far field vorticity and strain rate by this partitioning equation. Stress within the inhomogeneity is related to the far field stress by this partitioning tensor. And these partitioning tensors, they look formidable, but all the quantities are already known. Strain rate partitioning tensor, stress partitioning tensor. We call these partitioning equations. But the equations are variably called concentration equations, localization equations, and interaction equations in the literature. We prefer to use the term partitioning, following Lister and Williams. The reason for that is, if the inhomogeneity is weaker than the surrounding material, strain may concentrate it, but stress is not concentrated. Stress is actually smaller than the outside. On the other hand, if this is a stronger area mechanically and the outside medium is weaker, the strain is more concentrated in the immediate material rather than in the body. So concentration, localization are not really descriptive. Partitioning is a better term for that. Interaction is a good term, but we use interaction for different forms of these equations. Partitioning equations are the backbone of micromechanics. Again, micromechanics is a new development of continuum mechanics. It's continuum mechanics for heterogeneous materials. Partitioning equations are essential for micromechanics. The well-known self-consistent viscoplastic model, VPSC model, the model for simulating the development of LPOs in polycrystalline materials like quartzites. VPSC model is fundamentally based on the partitioning equations. The idea is this. A quartz crystal in a quartzite, for instance, a crystal grain is approximated by an inhomogeneity. Because we have these partitioning equations, the strain rate in any crystal grain is related to the overall far field strain rate, capital E, by a strain rate partitioning tensor. Vorticity in a local crystal is also related to the macroscale overall vorticity and strain rate by a vorticity partitioning equation. We can relate the deformation in a crystal to the overall deformation, like the deformation in the shear zone. Of course, the surrounding material of a quartz is a quartzite or other polycrystal aggregates. They are not a homogeneous, uniform material. The idea to apply Eshelby's partitioning equations is to use the concept of homogeneous equivalent medium. In short, the heterogeneous material surrounding any individual crystal is replaced by a hypothetical homogeneous equivalent medium. The rheological properties of the homogeneous equivalent medium is obtained by homogenization. I discussed homogenization very briefly in session 2. I'm going to talk about homogenization in my next lesson in more detail. So we have homogenizations and partitioning to solve. And both of these equations are based on partitioning equations. And these equations are solved simultaneously. So it is the partitioned strain rate and the vorticity that dictates the lattice rotation of an individual grain. And the rotation of all individual grains leads to the lattice preferred orientation. Geological observations are usually on a relatively small scale in rheologically distinct elements. Our observation is always within an inhomogeneity. Our observations are related to the partitioned deformation within that inhomogeneity rather than the large-scale deformation. To understand the development of the structures that we observe, we need to understand partitioned strain rate and vorticity and stress, rather than just the overall stress and strain field. So the relationship is not single-scale. Another application that I'm going to talk about in my next lesson is homogenization. To determine the overall effective elastical viscous stiffness of a heterogeneous material from stiffness of constituent materials is called homogenization, and homogenization relies on partitioning equations. Partitioning equations has many other applications. Anything that is related to heterogeneous materials and multi-scale problems relies on partitioning equations. Our self-consistent model for the deformation of heterogeneous lithosphere is also built upon partitioning equations. More details will be covered in following lessons. But in short, a lot of geological problems satisfy the condition of separation of scales. That is, the observation is on a small scale, whereas the background deformation is on a larger scale. Because of this separation of scales, we are able to use the inclusion solution of Escherpes. Natural deformation, of course, it's not Newtonian, and we need to deal with this nonlinear rheology. We need to do homogenization and partitioning simultaneously, that is the self-consistence. And this approach is often referred to as the Escherpes formalism. Using Escherpes formalism, we can relate our observations on a smaller scale to the macroscale deformation on a larger representative volume element, and then eventually to tectonic boundary conditions. This application relies on partitioning equations. Thank you for your attention. I will continue this topic in the following 2 lessons.